Right, so you're staring at a pile of articles about HDI and SLP PCBs and thinking, where do I even begin? Feels a bit like trying to digest a tech manual, right? But hey, that's what we're here for. This deep dive's going to slice through the jargon, and trust me, by the time we're done, you'll be tossing around HDI and SLP like you invented them. And who better to navigate this world with us than our PCB guru right here? So first things first, what are HDI and SLP PCBs? Ever tried, just imagine, cramming all the streets and skyscrapers of New York City onto a tiny little postage stamp? That's HDI in a nutshell.
It's like high-rise architecture, but for electronics, right? HDI is all about squeezing a crazy amount of components into these teeny tiny spaces. I mean, without it, forget sleek laptops or smartwatches. Your smartphone would be the size of, like, a brick.
No kidding. And our sources get into the nitty-gritty, talking about microvias.
Yeah.
Basically, imagine microscopic tunnels that connect the different layers on a circuit board. And get this, they can be blind, buried, or even stacked on top of each other.
Oh, yeah, and we're talking about lines and spaces on these boards that are thinner than a human hair, sometimes less than 0.1 millimeters. The precision is just, it's mind-boggling.
Okay, so HDI, we've got that down. But then the articles start mentioning SLP, substrate-like PCBs, and things get even wilder. It's like shrinking that postage stamp city down to the size of, I don't know, a grain of rice, maybe.
You know what? A grain of rice? That's actually a pretty good analogy. SLPs are the next generation, taking that density even further, and believe me, we're talking line widths and spacings smaller than a single red blood cell.
One of the articles even asks, is it a PCB or an IC substrate? Now that really caught my eye. It's like SLPs are blurring the lines between what we traditionally think of as a circuit board and something closer to a microchip itself.
It really is a fascinating evolution. You're spot on. SLPs are like this bridge between the world of PCBs and integrated circuits, pushing the boundaries of what's possible in electronics manufacturing.
So it's not just an upgrade, it's a whole new way of thinking about PCB design, it seems. But before we get too far ahead of ourselves, let's talk about the why. What challenges do SLPs overcome that traditional PCBs just can't handle?
One of the biggest hurdles is something called CTE mismatch.
CTE mismatch. Okay, you're going to have to break that one down for me. I'm picturing mismatched socks here. And in the world of electronics, that doesn't sound like a good thing.
Not quite, haha. CTE stands for coefficient of thermal expansion. Basically, different materials, they expand and contract at different rates when the temperature changes. Now imagine, in a tiny, densely packed SLP, you've got all sorts of materials crammed together. If their CTEs aren't playing nice, well, you get components cracking, connections breaking, a recipe for disaster.
So it's like building a house where the bricks and mortar are, like, expanding and shrinking at different rates.
Yeah.
Recipe for disaster.
Exactly. And SLPs, they're designed to handle that. One of the articles, it highlights how SLPs actually bridge the CTE gap between the PCB, IC substrate, and the die. They use materials and techniques that minimize those differences. And what does that mean? More reliable devices that can take the heat literally.
So they're not only smaller and more powerful, they're tougher than your average PCB, too. Impressive. But what about heat dissipation? All those tiny components crammed together, they must generate a ton of heat.
Absolutely. Heat's a real challenge in electronics, always has been. But SLP designers, they've got some tricks up their sleeves. One interesting thing they do is embed these, get this, copper coins within the layers.
Copper coins, like actual currency.
Not exactly, haha. Think of them more like tiny radiators. Copper is a fantastic heat conductor, so these coins basically pull the heat away from the critical components, preventing those damaging hotspots.
It's like giving those hardworking components their own personal AC units. So clever.
Right. It's not just about making things smaller, it's about solving those real-world engineering challenges, but with, a little bit of creativity. And this actually leads into something we see mentioned a lot in our research, mobile phones as a major driving force behind SLP development.
Yeah, one of the articles even specifically called out these mobile phone giants, which makes sense. I mean, smartphones are all about packing a ton of functionality into a device that fits in your pocket. Every millimeter saved on the circuit board means you've got more room for, I don't know, a bigger battery, a better camera, you name it.
Exactly. And don't forget about the performance demands we put on these things these days. High-resolution gaming, streaming 4K video, those AR apps that everyone's talking about, none of that would be possible without SLPs.
Wow, so next time I'm scrolling through my phone, I'll be thinking about those tiny, invisible components working their magic thanks to HDI and SLP.
It's pretty remarkable when you stop and think about it. But speaking of remarkable, you mentioned getting ahead of ourselves earlier, and I think it's time we actually delve into the world of SLP design itself.
Okay, let's do it. What are some of the challenges that come with designing in such a mind-bogglingly small scale? I mean, it can't be as simple as just shrinking everything down, right?
You're telling me designing with SLPs, it's not for the faint of heart. It's like trying to assemble a jigsaw puzzle under a microscope where the pieces are constantly trying to melt.
Sounds intense.
One of the biggest differences is you're not just placing components on a board anymore. You're practically weaving them into the fabric of the SLP. It's about thinking about die placement, those tiny bonding pads, and how it all interacts, both electrically and thermally.
So much more intricate than traditional PCB design.
Yeah.
It's like the difference between playing checkers and 3D chess.
Exactly. And then there's the thermal management aspect, which, as we've established, is absolutely critical. We talked about copper coins, but designers use all sorts of tricks. Thermal vias, carefully routed traces, even tiny heat sinks.
So SLP design is as much an art as it is a science.
You could say that. It takes a deep understanding of both electrical and thermal engineering, combined with a whole lot of creativity and serious problem-solving skills.
It sounds like SLP design is in a league of its own compared to traditional PCB design.
It definitely adds a whole other layer of complexity, that's for sure. But the payoff, the ability to pack so much functionality into such small spaces, it opens up a world of possibilities for electronic devices.
This is what I want to know. What's the big picture impact of this technology? We're knee-deep in the weeds talking about HDI and SLP, these tiny tech wonders that most people probably don't even realize exist.
It's true. HDI and SLPs, they're kind of like the unsung heroes of the electronics world, wouldn't you say? Quietly powering the devices we use day in and day out, and shaping the future of tech while they're at it.
Okay, so paint us a picture here. How are they doing that? What's the big picture impact?
Well, think about it. What's the trend been in electronics, like forever? Smaller, faster, more powerful. And HDI and SLPs, essential to making that happen. They're the reason we can have smartphones that fit in our pockets, but pack more computing power than those bulky computers we used to have back in the day.
Right, remember when cell phones were just for making calls?
Yeah.
And they were the size of a brick. Now my phone's like 1,000,000 times more powerful and it fits in my hand. It's kind of mind-blowing.
And it's not just about size and performance. HDI and SLPs, they're also driving down costs, making these incredible technologies accessible to, well, pretty much everyone. It's why we've seen such an explosion of, affordable, feature-rich electronics in recent years.
That's a great point. So even though HDI and SLP might seem, I don't know, super high-tech and expensive at first glance, they're actually making electronics more affordable for everyone.
Exactly. And as these technologies keep evolving, we're going to see even more innovation and even more affordability. It's an exciting time to be into tech, that's for sure.
It really is. Speaking of costs, though, I noticed in our research that SLPs, while maybe more expensive to produce initially, can actually lead to cost savings in the long run. How does that work?
That's a really sharp observation. It all comes down to this idea of cost per function. And it highlights the kind of calculations that companies have to make when they're trying to decide between HDI and SLP for a product.
Cost per function. Break that down for us.
So SLPs, more expensive to manufacture upfront because they require such advanced materials and techniques. But, and this is a big but, they can cram so much more functionality into a smaller space. You might end up needing a smaller, less complex SLP to achieve the same performance as a, larger HDI board.
So it's like instead of building a sprawling single-story house, you're building a super efficient high-rise that takes up less space.
Exactly. And that translates into savings on materials, assembly, even shipping, because you're dealing with a smaller, lighter product. It's like that old saying, good things come in small packages, right? But in this case, it's more like cost-effective, and powerful things.
I like that saying. But I imagine it's not always a clear-cut decision. When would a company choose HDI over SLP? Or vice versa.
Right. Like with anything in engineering, there are trade-offs. Sometimes you absolutely need that extreme miniaturization or that raw power that SLPs offer, and the added cost is worth it. Other times, a more traditional HDI approach might be more practical, more budget-friendly. It's a balancing act.
High-tech balancing act, for sure. So like we've been saying, HDI and SLP, they're more than just, obscure acronyms in a tech spec sheet. They're shaping the way our electronics look, feel, and perform every single day. My mind is racing with possibilities here. We've covered how HDI and SLP are already making electronics smaller, but it sounds like we're only just scratching the surface of what's possible.
Oh, absolutely. Remember those 30-micrometer line widths we were talking about? Mind-blowingly small, right?
Yeah.
But the thing is, Researchers, engineers, they're always pushing further, always experimenting with new materials, new manufacturing techniques, trying to create even smaller, even more densely packed circuits.
Hold on. Smaller than a red blood cell. We're talking about components that are practically invisible. What are the challenges there? I mean, how do you even work with something you can barely see?
That's the exciting part, right? It's like discovering a whole new world of engineering challenges. Heat dissipation, that's a big one, becomes even more critical at those sizes. And then we'll need like totally new ways to test and inspect these circuits. Plus, imagine the design process at that scale. The software tools alone, they'll need a serious upgrade.
It's like we're talking about building, I don't know, a whole city on the head of a pin. And not just any city, a city that has to function perfectly with its own power grid, everything.
Perfect analogy. It really is a whole new frontier in electronics engineering. And as these HDI and SLP technologies, they keep evolving, they have the potential to revolutionize so much more than just our phones and laptops.
Okay, now you've got me really intrigued.
Yeah.
What else is on the horizon? What are some of the potential applications beyond what we've talked about?
Well, think about the medical field for a second. Imagine tiny biocompatible sensors, so small you could implant them in the body to, I don't know, monitor vital signs in real time. That kind of continuous data could totally revolutionize healthcare, allow for early detection and treatment.
That's amazing. It's like having a microscopic doctor inside you 24/7.
Exactly. Or what about aerospace? Lighter, ultra-efficient electronics that can withstand, like, the extreme conditions of space, that could allow us to explore the universe in ways we haven't even dreamed of.
Okay, now we're talking about spaceships that are lighter, more powerful than ever before, and it's all thanks to these tiny components.
And that's just, like, the tip of the iceberg. We're talking energy, transportation, manufacturing. HDI and SLP, they could be the key to solving some of the biggest challenges we face.
It's amazing to think that something so small could have such a huge impact.
It really is a testament to, human ingenuity that we can create these amazingly complex systems at such a tiny scale.
It really is. Well, I have to say, this deep dive has been quite a journey. I went from feeling, honestly, a little overwhelmed by all the technical jargon to being completely fascinated by the possibilities of HDI and SLP.
Always great to see that spark of curiosity.
So to anyone listening who's ever felt, a little intimidated by technology, I hope this deep dive has shown that even the most complex things, you can break them down, you can understand them, and hey, who knows? Maybe you'll be the one to come up with the next big breakthrough in miniaturization.
Now that would be something.
It certainly would. And to all of you listening, thanks for joining us on this journey into the world of, well, tiny but mighty technology. Until next time, keep exploring, keep learning, and keep asking those big questions.